Hi, this is the tutorial for assignment 5. I'll make some comments on the questions on optimization problems. Now question 1. So read question 1 first. For all the questions, we need to follow the step procedures listed in here. Step A through step G. Now question 1. The first thing we do is to understand the problem, and then we draw a sketch to understand the problem. A farmer has 480 meters of fencing, and he wants to make a pig pen, a rectangular pig pen. The pen is to have two internal fences that runs parallel to the end fences. And we are looking for the dimension. By dimension, we mean the length and the width that will produce the maximum total area. In step A, we draw a sketch. The farmer is trying to build a rectangular pig pen. There are two internal fences, right? Two internal fences. So now let's say two internal fences. The shape of the pig pen is something like this. So we are trying to find the length and the width. That's the length. I'll call that width. Okay. We are trying to find the length and the width that will maximize the area of the pig pen. That's the question. We're done step A. Draw a sketch. Understand the problem. And then in step B, we make a list of variables. We introduce the variables. So first of all, identify the quantity for which you want to maximize or minimize. In this particular case, we want to maximize the total area. So we need a variable representing the total area. We are going to use A, uppercase A, to denote the total area. So we say something like, let A, right, be the total area. Of the pig pen. And then we identify the quantity to be optimized depends on what quantities. Of course, the area of a rectangle depends on the length and the width. We'll call the length of the rectangle, the big rectangle, x. We'll use y to denote the width. I will try to label something. I will use x to denote the length. I will use y to denote the width. Again, in general, identify the quantity to be optimized. In this particular case, the quantity to be maximized. And then you identify the quantity to be optimized depends on which quantities. In this particular case, the width and the length. I believe these are all the variables we need to introduce. So maybe I can say let x be the length and y so be the width. And then in step C, in next step, we are going to get as many relations as possible. In step C, we make a list of relations. It's easy to see how to write A in terms of x and y. So the area of a rectangle is the length multiplied by the width. So one relation we can get is A equals x times y, right? Some people call this one objective function, the objective function. And we have another condition. The total fencing is 480 meters. The total fencing is 480 meters. By total fencing, we mean we have two axes. The bottom dotted line segment is x, has the length of x. The top one has the length of x. And altogether we have 3 y's, I believe, right? Yeah, because there are 3 sections, 2 internal fencings. So that's y, that's y. So look at the mouse cursor. That's also y. So we have 3 y's. So the constraints, one of the constraints is you do not have to care about the term. The constraint is the relation between the variables. Okay, so we have 2x, and then plus, sorry, it's not 3y, 4y's, right? 1, 2, 3, 4, 4y's. Equals 480. The unit is meters. So because the total fencing is 480 meters. So with the total fencing of 480 meters, he's trying to build a rectangular pig pen in something like this. Now we have all the possible relations. In step C, you can get as many relations as needed. So we're done step C. And then in step D, so basically in step D, we want to write the quantity to be optimized as a function of only one variable. In this particular case, we want to write A. The area is the quantity, so to be maximized, we want to write A as a function of only one variable, either x or y. I'll move on to the next slide. To write A, the quantity so to be maximized as a function of only x or y, all we need is to solve the second equation for, so now let's say x, and then we can write the A as a function of only y. Okay. Now let's do that. Okay. Now in step D, I'll call the first one equation 1, the objective function, the second one the constraint. That's a relation between x and y. I'll call the second equation equation 2. Okay. We'll solve the second equation for x. Now from equation 2, okay, we can solve the equation for x. I believe we are going to have x equals, if you divide two sides of the equation by 2 and then you move 4y to the right hand side, I believe we're going to have y minus, sorry, we're going to have 240 minus 2y. I believe all of you guys can understand that, right? Solve the equation for x, write x in terms of y from equation 2. And then I'll call the new equation equation 3. And then we plug equation 3 into equation 1. So basically I want to write A, the quantity to be maximized as a function of only y in this particular case. Only one variable y. Okay. So maybe we can say we plug equation 3 into 1. We have A, the quantity So to be maximized, the area is the quantity, right? A can be written as, I'm going to replace x with 240 minus 2y. So we have 240 minus 2y. Yeah, that's x, right? And then multiplied by y. At this point, I can write the a as a function of y. So because a is only dependent on y right now, I can write a as a of y, right? I hope it's not too messy. So I think we have done step D. Now let's look at the step, okay? Eventually, we want to write the dependent variable, the quantity to be maximized, as a function of only one variable. Yeah, that's the meaning, okay? In step E, we are going to get the domain of the function using the meaning of the question. I will show you what I mean. Now the problem is going to be the problem find the maximum value of a. A is a function of y. We're going to determine the domain of the function. So basically, the largest possible value of y and the smallest possible value of y. Okay. If you go back to the picture, y, it means the width of the pick pen. You can imagine the value of y can be as small as possible. It cannot be 0, but it can be as tiny as possible. You just build a pen very long horizontally. If you know what I mean. If you do a pick pen, something like this, so very, very long. Still, it's possible to have two internal fences, right? I'm trying to say the value of y can be any positive number, okay, but it cannot be 0. Y value is greater than 0. So y can take any positive value greater than 0, right? And then we are going to identify the largest possible value of y. Try to understand the following. The least possible value of x will give you the largest possible value of y. You just imagine it's possible to build a pig pen with the 480 fencing. Yeah, something like this, very long vertically. Yeah, that way, right? You can still have two sections. Okay, that's also a pig pen, but the x value is going to be very tiny. Now we're trying to find the largest possible value of y. Think about it. The least possible value of x will give you the largest possible value of y. So does that make sense? Now the least possible value of x is 0. Okay, I'm trying to say the largest possible value of y is determined from that equation using x value of 0. So because the least value of x is a positive number, very close to 0. So basically, you set x value to be 0, and then you solve the equation for y. I believe the value of y is 120. 480 so divided by 4, you have 120. That's the largest possible value of y. That's what I meant by finding the domain of the function, okay, using the meaning of the question. Okay, now the problem has been converted to a math problem. So we're going to maximize a is a function of y when the value of y is in between 0 and 120. At this point, you can follow the routine, follow the knowledge, follow the step procedures we have learned last time. So question 2 is a question on the course manual. You read the course manual. I believe you can see the question. I have the solution to question 2. So just the solution is kind of not in details. You show more work. Okay. Now I'm going to make some comments on question 3. On the screen, you have question 3. Again, in step A, we try to understand the problem by drawing a sketch. You are trying to have a poster, right? You know the total area of the poster, it's 200 inches, square inches, I mean. When talking about the area, you say square inches, square meters, square centimeters, and so on, right? And you know the margins. You know the side margins, 1 inch, and you have 2 inches of 2 inches margin on the top and 1.5 inches margin at the bottom. Okay. Now what we are doing is we are looking for the dimension. Again, dimension. Okay, we are looking for the length and the width that will produce the largest print area. And by the way, so there's a typo. It's print area. It's not printed area. Print area. Okay, now let's try to draw a sketch. So try to understand the problem. In step A, let's draw a sketch. You are going to have a poster. The poster is a kind of rectangular shape. Something like this, right? And then you have the side margins. The left margin is 1 inch, the right margin is 1 inch, right? And the top margin is 2 inches. And the bottom margin is 1.5 inches. It's kind of something like this. Illustration only. The shaded region is the print area, right? If you want me to label something, the bottom margin is 1.5, right? 1.5 inches. And the side margin is 1 inch. And the top margin is 2. Inches. Okay, so that's the meaning of the question. Of course, as long as you have the total area of 200 inches, and then you can build the poster either very wide or very narrow, right? Now the problem is how to build a poster so that the total area, I mean the print area, is the largest. Yeah, that's the problem. Okay. So we're done with step A. Now step B, we're going to introduce the variables. If you look at the question, we want to maximize the print area, right? to introduce the variables, the same as before. It's always the same. Identify the quantity to be optimized. In this particular case, the quantity to be maximized. Okay. So maybe we let A be the print area. Use a notation to represent the quantity to be maximized in this particular case. And then we identify the quantity will depend on what? It's relevant to the question 2. So we are looking for the dimension of the poster. We are looking for the dimension of the poster, right? That will produce the largest print area. I'm going to call the length of the poster x, because we are looking for the dimension of the poster, right? And I'm going to call the width of the poster, the total poster, y. I write it down. Let x be the length of the poster. And let y be the width of the poster. So we're done step B. In step B, we introduce the variables. Again, identify the quantity to be maximized in this case. It's A, right? And then you identify A, the quantity, so to be maximized. So depends on what quantity is. So depends on the length and the width of the poster. So because the margin is fixed, as long as you have as long as you can determine the length and the width, and the print area is fixed, you are going to see so. Now in step C, we get as many relations as possible at this point. We write the quantity to be maximized, the total area, as a function of x and y first. Okay. Try to understand that A is the area of the shaded region, the print area. Now the area of A is given by x minus the two side margins, the left margin and the right margin, x minus 2, so that makes sense. X minus 2 is the length of the print area. I'll say that way. And then the width of the print area is y minus the bottom margin 1.5 and then minus the top margin of 2, right? It's y minus 3.5. .5 is the total of the bottom margin and the top margin. That's how to write A as a function of x and y. The objective function. And then the first condition will give you the constraint. So we know the total area of the poster is 200 square inches. The total area of the poster is x times y, so that makes sense. The length of the poster and multiplied by the width of the poster. So x times y is equal to 200. Using the first condition. These are probably all the relations we can get we have written the quantity to be maximized as a function of x and y. We also have a relation between x and y. Okay, so we're done step C. Now, in step D, we are going to write a as a function of only one variable. That's the meaning of the next step. Now in step D, in order to do that, if you want to write the a as a function of only x, you can solve the second equation for y, right? And then you write y in terms of x as 200 over x. I'll show you some more details. Okay. I'll call that equation 1. I'll call the second equation equation 2. From equation 2, we can solve the equation for y, right? We have y equals 200 over x. All of you guys can see that. I'll call that equation 3. And then we plug 3 into equation 1. We're going to have a, the area of the poster, the area of the print area. A equals x minus 2. And now y can be replaced with 200 over x, and then times 200 over x minus 3.5. At this point, we can write a as a of x. So because a is dependent only on x now, right? And probably I can show you one more step. So because the next step could be a little bit confusing. Okay. In step E, we identify the domain of the function. So by that we mean the least possible value of x and the largest possible value of x. You look at the mouse cursor. You look at the sketch. X is the length of the poster. So because there have to be two, the left margin and the right margin, the two margins will take 2 inches. So that makes sense? So the least value of x should be 2, because the two margins, they have to be included. You just imagine you build a poster very long vertically. Okay. It cannot be 2, but it can be any number very close to 2. So we'll say x is greater than 2. Now, in step E, we're trying to get the domain of the function, right? The same as before, the largest possible value of x is determined by the least possible value of y, right? And then you think about the least possible value of y. It cannot be 0, so because you have to have a top margin of 2, the bottom margin of 1.5. So the least possible value of y is the total of the top margin and the bottom margin, so which is 3.5. Now remember, the least possible value of y is 3.5. And you have a relation between x and y in here. You use the least possible value of y, 3.5, to determine the largest possible value of x. It's not part of the work, but I will squeeze that in here. Okay. Again, the largest possible value of x is determined by the least possible value of y, and the least possible value of y is very close to 3.5. We're going to use y value of 3.5 to determine the largest possible value of x. Okay, so you solve the equation that x times 3.5 so equals 200. Solve that equation for x, so you have the largest possible value of x. So x is equal to, you divide two sides of the equation by 3.5, and then you multiply the numerator and the denominator by 2 to write a nicer fraction. I believe the value of x is going to be 400 minus, so divided by 7, 400 over 7. Okay, I'm trying to tell you the largest possible value of x is 400 over 7. So we're done step E. Okay. At this point, the problem is converted to a math problem of maximizing A when x is greater than 2 and less than 400 over 7. I believe you can move on from here. A little bit more hint. In order to get the critical number easily, for the right-hand side of A of x, you'd better multiply them out so that each term is either a constant or a power function of x. So it's easier to differentiate. Alternatively, in order to get the critical number of A, you can also use the product rule. It's possible, but it's going to be harder. I'm trying to say multiply out the function first before differentiating. Okay. These are probably all the comments I want to make. So that's all for today. Thank you.